Okay. Okay. So we are going to study about Markov models. So in the previous class, we saw some things about Markov model. Like we saw the recurrent neural network, which has time dimension. Basically, it has some memory and it depends on its own previous state. So in that way, it has a memory, and it it takes care of time evolution also. Let's today see Markov models in more detail. Let's say I have a process or a signal which the current value depends on its past values also, right? I have some signal or some input or something where current value also depends on the past values. Can you give an example? Can you give an example? Okay, some more practical, not mathematical, but okay, practical means use here. I'll give a very crude example to start with. What is your current position, GPS location? It depends on what was your position 1 minute ago, right? If you were in the stairs 1 minute ago, now you are here. It is not possible that after 1 minute you are in your hometown, if it is not in Kanpur. If your hometown, maybe it's in Bombay or Bangalore or Madras, right? So there is a dependence in temporal dependence. So if you are today, you are at this instant you are one minute ago, if you are in the stairs, after 1 minute, maybe at most you are in your hostel, but certainly not in Rawatpur. In 1 minute you can't reach Rawatpur, right? So here your GPS location has a temporal dependence. What else? More examples. Temperature. Today's temperature, if yesterday it was maybe 25 degrees Celsius, average temperature, or maybe temperature at 2 o'clock, 2 p.m. exactly. If yesterday at 2 p.m. it was 20 degrees Celsius, it's very likely that today it will be also close to 20 degrees Celsius only. It won't be suddenly 0 degrees Celsius, right? Or it won't be suddenly 50 degrees, 45 degrees Celsius. Or let's take the average temperature during the daytime. Average daytime temperature, there are some fluctuations, no doubt about it, but it won't be, basically it is a dependent process, time dependent process, right? It depends on its previous values. Or it can be modeled to depend on its previous values. If I give you temperature for 1 week, I ask you what is the temperature next week, you can very likely you can predict it. That's how forecasting works, right? Weather forecasting. What else?
Product sales.
Product sales, yes. So if
For example, if there weren't much sales the past day, if it is in some temporarily seasonal period, then and we can detect that the slowdown period has started based on the decreasing trends from the past 5 years.
yes, yeah. If I give you the data for daily sale for 1 week and I ask you what is the value of sale on this particular next day, you may predict it very easily.
Seasonally, like
Season?
I mean the pattern of rainfall.
Pattern of rainfall, yes.
That repeats again.
Yeah.
Movement of weather activity like storms or
So all meteorological parameters. like rainfall or other storms or temperature, pollution. What else?
Stock market.
Stock market. Stock market. What else? Okay, so think of more examples, and you can certainly come up with many more. Okay, so how can you model? Let's say if I ask you the question, tell me the weather tomorrow, tell me the temperature tomorrow, and you know the temperature for all the past. You have data for more than 5 years in the past, up till today. I ask you, what will be the temperature tomorrow? What kind of model can you build? What kind of model can you build? You have done machine learning, Markov model. No, I would have said LSTM or RNN. No, an RNN I can build, or I can build a CNN, 1D CNN. Right? 1D CNN can be built. So let's start with something of that sort. I can say my xn, which means my x is some observation, maybe temperature or rainfall, whatever, and n is the time instant. It's discrete time. Right? So nth instant, which means, let's say, today or tomorrow, let's say. This is equal to, this could be a deterministic model. F of right. So my x of n, let's say the temperature tomorrow, it depends on temperature 1 day before, 2 days before, 3 days before, so on and so forth. And it's a deterministic model, which means, for example, a linear model or an affine model. Right? This is an affine model. It's a deterministic model. Right? How many trainable parameters or how many tunable parameters are there? K plus 1. So k here and 1 here, k plus 1. Tunable parameters are there.
Excuse me, sir. Sir, if we always append a 1 to the input data vector and then combine the bias and the weight vector with that 1 appended, then would that type of a transformation always be linear? Instead of adding a W0, we always, whatever data we receive, we append a 1 to it, and then the weight vector will already have that W0 in it. So when we do the inner product, then W0 will be there.
It's an affine transformation. No? It's an affine transformation. For linearity, that condition is required. So that's the only criterion for linearity. In casually, you may say it's a linear model. Like we have also said it in the past. Casually, oh, it's a linear model, but actually, it's a affine model, more strictly speaking. Okay. Now, these are deterministic models. We have seen some of them in the past, like CNN or 1D CNN, etc., etc. But now, and even LSTM also is also a kind of this deterministic model, right? Now, we are going to another kind of models, which are probabilistic model. Whenever you hear the word probability, what comes into your mind? First thing that comes into your mind. That is an example, yes? Huh? Gaussian, okay, I think you are already there. So I was looking for an answer, it's called random variable. So here, my xn is no longer a deterministic number, deterministic parameter variable. It's a random variable. So which means it has got some PDF associated with it, or if you call it probability distribution function or probability density function. We will work with probability density functions only. Okay. So my PDF could be P of xn. Now what happens is my P of xn, if I want to make it dependent on the past, these random variables also, it will become a conditional PDF, right? Conditional PDF is xn given xn minus 1, xn minus 2, so on and so forth. This is a probabilistic modeling. Same thing, deterministic, probabilistic, right? Can you give an example? Can you give an example like the Gaussian or normal distribution? How will you actually model it? If you want to model the rainfall tomorrow or temperature tomorrow, what kind of model can you make? Any simple model suggest. Like here you saw example was in a fine transformation. What example will you take here?
So we can build a kind of Gaussian model in which we keep updating the mean and variance every day using the past data.
Okay, what's your name?
We
Vineet. Thank you, Vineet. Very good. Yeah, let's do it. Let's take it as a Gaussian model. Normal. Xn is my random variable. It has some mean and variance. My mean is a function of xn minus 1, so on. Sorry, xn minus 1, xn minus 2. And my variance is also a function of that's a probabilistic model, right? Simple thing. It's a distribution over xn, and my parameters of this distribution, they depend on these past inputs. It could be either moving average thing, what you suggested, it could be any other algorithm to estimate mu and sigma. Here I can use now DNN, RNN, CNN, or linear regression, whatever you like, you can use here. Right? So this is an example. Okay. Now you see here, this becomes a very large number of variables. This model becomes very large. You have to have some way to curtail the size. How many parameters are there? So that depends on number of parameters here and number of parameters here. Could be very large. So we can make a simplification. I will say, just tell me what was the temperature yesterday. Based on that, I will tell you what is today's temperature. I don't need 5 years of data. Means I don't want to use 5 years of data to predict my temperature tomorrow. I only need past 1 day data, or means today's data. That's it. Or maybe today's and yesterday's data. Just 2 days data you give me, I'll predict the next day data, and I will keep doing it every day. But I don't want to use my computer to process 5 years of data every day, right? So then I go to Markov models. So what are Markov models? My P of xn given xn minus 1, so on and so forth. This is equal to simply, that's it. I am saying my xn is conditionally independent of xn minus 2, xn minus 3, so on and so forth, which means if you give me xn minus 1, if you condition this variable on this variable, then every other variable can be ignored, which means this is independent of everything else. This is called first order Markov model. Right? So it's an approximation. It could be exactly true or it could be approximately true, but that's what it is. Right? Now somebody may say, no, just don't give me 1 day data, give me at least 5 days of data, then I will be able to predict tomorrow's We say, okay, no problem, take that. So you say this is P of xn is dependent on xn minus 1, so on up to xn minus some capital M. This becomes an mth order Markov model, right? An mth order Markov model means that this conditional distribution, conditional PDF is actually, it depends only on these random variables and conditionally independent of all other random variables. Right? That's an mth order Markov model. Right? You can decide what order you want. Right? Okay, a quick question just to shake you up. Somebody suggested here sales. Who said sales? Aditya. Sanreet. You said sales. So let's say I am selling something today. You want to predict what will be my sales tomorrow. Can you predict how much past data do you need to predict that? One month? Okay.
Based on the scale of this commodity, you would need more data or less data, because
Okay.
if it is high frequency, it is a highly frequent sale, then we need like 2 or 3 days of sufficient. But if it's a low frequency item, then we need more data to cover the possibility and see if there are overlaps.
Yeah, good assessment. Yes. I'll give one example here. There is something called in America. I have seen Christmas. What happens in Christmas? Everything, like sales go up, like they shoot in 1 or 2 days. Like there is a Christmas period, Christmas holidays, around 25th, 26th, 27th of December, and suddenly everything, the sale has a peak. And also the companies like Amazon, etc., they give some special discounts in those periods so that sales are kind of more higher. So suddenly you are seeing the sales are like 100, 100, 150, 100, 110, and suddenly you see 20,000 on 25th of December. So which means if I make a model which depends only on a few days of data or even months of data, it's not sufficient. You may need to see the trend over the entire year, and you will see every time on 25th of December there is a peak, and it continues for some time and then it dies out. Then you can say, okay, on this 25th of December, I'll be having a peak. So just to show you that these Markov models are approximations. They're not exactly how the world works. Okay. Now let's talk about the representation. How do we represent these models graphically? This is a random variable called x of n. This is a random variable called x of n minus 1. This is a random variable called x of n minus 2. How does the dependence look like? So my x of n, let's talk about first order Markov model. I'm talking about the first example first. xn depends only on xn minus 1, and it's independent of everything else if you tell me xn minus 1. Right? That's how I represent it. Xn minus 1 depends on xn minus 2 only and is independent of everything else. You can go back in time as much as you want. This is a first order Markov model. Do you understand? If I give you this notation, can you write this PDF, this conditional PDF? Yes? It's simply, you know how to map. And if I give you this PDF, can you write the graphical model? Yes? Let's do some exercises to make sure that you understand it very nicely. Write down second order Markov model. Make the circles. Write down the second order Markov model. Write down the second order Markov model, both the PDF as well as the diagram of the graph. there's so many intersections here. It's not clear what is coming in, what is going out. Yeah, but it's correct. Yeah. It's correct. What's your name? Akshat. Okay, I think I saw many of you have already completed it. It's correct that, right? My xn depends on xn minus 1 and xn minus 2. And my xn minus 1 depends on this and this. So let's draw it. And this one depends on this and the previous one. So this is my second order Markov model. Right? Some people, they have drawn it downwards, which is looking aesthetically more beautiful. So second order. This is the first order. Okay. Likewise, you can draw for any mth order. In general, this is called graphical representation of PDFs. Okay. Now, here you have seen how to write PDF, conditional PDF of a single random variable. Sometimes you are given the joint distribution, or I may ask you to write the joint distribution. Probability of xn, let's take it as capital N. What is this? This is a joint PDF of random variables x1 to x capital N. Use first order random variable to factorize this joint PDF. Use a first order Markov model to factorize this joint PDF. How will you factorize it? Chain rule, very good. And then you have conditional independence. So use both of them to factorize it. Can you do that?
What do we assume x1 to?
Yeah, good question. So leave it as p of x1, means because you don't know its dependence on anything else. So, okay, we can write it as p of x1, p of x2 given x1, p of x3 given x2 x1, so on, p of x capital N given x capital N minus 1, x n minus 2, so on and so forth up to x1. I can write this as this. Any assumptions involved here? Are there any assumptions involved? No assumptions involved. Like this is, I can always write it like this. Now I will apply those conditional things to simplify this this thing. So I can write this as p of x1, p of x2 given x1, x3 given x2 only, and so here you have now 1D Markov model assumption involved, right? This is for if first order Markov model. If first order Markov model, then you can write this as this. Which means if you are modeling this as a first order Markov model, nobody will tell you. Right? Nobody will tell you that use first order Markov model. This is your model, your assumption. And how true or how false it is, you have to check. You are responsible for that. Okay, now you can simplify it as this. Right? Can you write it like this? This is the product P xn given xn minus 1 n goes from 2 to capital N, right? And but this px1 remains out, and it stands out, right? Is that clear? This is a simplified notation. And likewise, you can write for other notations also. Okay, now time to think. If you are using 1D CNN, your dependence on past inputs is like a finite impulse response filter, right? It's a very finite impulse response, which means it has a finite memory. My current input can only depend on a finite number of previous inputs. Or my current output can depend only on a finite number of previous inputs. But if I want to have really long memory or long or infinite impulse response kind of filter, what do we do? Some kind of recurrence is added, or even more fundamentally, some kind of latent variables are added, right? Some kind of latent variables. Okay, I will just show you the example here. Okay, can you write the joint PDF? Can you write the joint PDF of P of so there are random variables are here, n, xn and zn, everything. How do you write the joint PDF? Done? So in this, you don't have your notebooks. Bring your notebooks, you will learn better. Okay, now we give a special concession in the class that you are free to copy from each other. Copy means discuss, collaborate. You think that something you not understood, feel free to ask questions, of course to me, but also when I give some exercise, feel free to discuss amongst yourselves and solve it. So maybe you can make pairs or triplets, whatever you want to make, and feel free to write the answers. Learn from each other, collaborate. But understand, don't copy, just don't blindly copy, but understand from each other. If you have a good friend who understood and you not understood, no problem. Discuss and learn from it. We make some groups, groups of 2 or 3, whatever you want. You want to be in some group? What's your name? Shrey. Who is Shrey? Shrey. Who is Shrey? You want to make some group with some other Shrey or not Shrey person? Don't sit alone. Sit with somebody and feel free to discuss and ask questions and help them and get help. Okay, as we move on, my questions will become a little more difficult, so I would recommend make some groups. This was an easy question. I will write down the answer. Anybody has written? Raise your hand. Which group has written? You two are together? Huh? Together? At least one correct answer I found. So this is P of X. Okay, he used I, so I will also use I. Given Zi, P of Zi given everybody wrote this answer? You can make groups, means please make groups. Be together, no problem. Okay. Now tell me, my xn, does it depend on xn minus 1? Does it depend on xn minus 1?
There is a correlation, but
okay, let's say if I tell you my xn minus 3 is this, xn minus 2 is this, xn minus 1 is this, tell me what is xn. And I don't tell you these values. I just tell you xn minus 3, xn minus 2, xn minus 1, and I ask you what is xn. Will this value depend on these? How many of these will it depend on? All of them. How? Through Z. So that is the benefit of using latent variable models. So Z is a latent variable. So my Z is a latent variable, and it is kind of saving all the information. And if I tell you what value of Zn, then you can throw away everything else. If I tell you the value of Zn, xn can be simply known from here, or the PDF of xn is known from here, and you can throw away all these things. Right? But to know this value, you need to know this. Okay? Or if you know this value, then also you can throw away this, because from this you can estimate this, from this you can estimate this. Right?
So can we actually say that xn is independent of xn minus 1 or xn minus 2?
In this model, it is not independent. It is conditionally independent. If I give you this condition, if I give you this, then it is independent. Otherwise, it is not. Okay. So this is called a hidden Markov model. What is Markov here? This chain is Markov. So which means Zn depends on Zn minus 1, Zn minus 2. This thing is Markov. And this is called hidden Markov model because this is a latent variable or a hidden variable. You don't see it, you may not see it directly. You are only seeing x. But this thing is the latent thing which is capturing all the information. I think at this point of time, I will give you some examples. So in hidden Markov model, the requirement here is Z must be discrete. Or Zn, whatever, Zn minus 1, everything, they must be discrete random variables. They cannot be continuous random variables. All of you understand what is discrete random variable? Understand? Discrete random variable means it can take discrete number of values only, like flip of a coin. It can be either heads or tails, nothing in between. You can't say it is 70% heads and 30% tails. Right? On the other hand, continuous random variable will take continuous values. Let's say temperature tomorrow. It can have any value in the range of whatever 0 to 50, I think in India. Right? So it's a continuous random variable, but coin flip is a discrete random variable. So Zn must be a discrete random variable in a hidden Markov model. X can be anything. X can be discrete or continuous, doesn't matter. Right? Now, let's have some examples. All of you told about weather forecasting. What could be the Z here? It's the requirement of hidden Markov model. Hidden Markov model does not deal with continuous Zs. It only deals with discrete Zs. If you have a continuous Z, then you get some other model. I think it is conditional random fields CRF model. I don't remember. So, but that's a different model altogether. So my hidden Markov model requires that to be discrete. In weather forecasting, of course, this Z could be a statistically derived quantity. It may not have any real kind of term associated with it. But just to understand the concept, we can also have some concepts like in weather forecast, what could be my discrete random variable? Or hidden, what could be my hidden random variable? Huh? Date could be a, which means if I tell you the date, you can tell me the weather. Huh? Average temperature. Yeah, date can tell you, huh? Month.
So the latent variable should not be obtainable by any observational method.
You can estimate because there is a dependency, no, between x and z. If you are given p of x given z, can you tell me p of z given x? How?
By base rule.
Base rule. Yeah, there is a dependency.
No, but sir, in the actual like a problem statement format, if we are given some features in the raw data, then when we are wanting to assume hidden variables for this raw data, then this set should be exclusive of this set, right?
Once again,
the set of hidden variables and any hidden physical variables we assume should be exclusive of this set of observed variables in the data set. Right? We cannot take up variables from the data set and call them hidden, or can we?
then they're not hidden, but they're already observed.
So for example, in case of the weather forecast, we always know that what is the date or the time and the geographical coordinates. So
You may not know. Maybe I will tell you, oh, it was a sunny day and the temperature was 45 degrees Celsius. Tell me which month it was. Right? Maybe some situations like that. So yeah, date or month could be, but something more relatable could be season. Right? If I tell you it was summer season, then you know, okay, maybe the temperature PDF is something like this. Yeah, season or month, both are fine. Because both are very much correlated. Actually, season, there is nothing like season. It's just a created thing that, okay, because temperature is in this range, so let's call it summers, let's call it winters, let's call it. Because if you go to Australia, there the seasons will be different, right? The temperature patterns are so different there. So season is a kind of construct which captures the weather. I do ASR, automatic speech recognition. What could be my latent variables? Which means if I say something, my speech has got some what do you say, spectrum, some frequencies, some, so they depend on what? Something hidden, something unseen. Huh? MFCC, you observe from your data. I take your speech and I perform a transform.
Distance from the recording.
Yeah. Yes. Yeah. A distance will certainly change the amplitude and some maybe distortions can come in. Yeah.
Intensity with which the drum of that microphone was videoed.
The intensity at the source, it could be but then it is a continuous random variable. Distance also is a continuous random variable. Yeah. So you can't use HMM for that. Discrete.
Speech,
Speech recognition.
male or female.
Filter and this the observation is sound. So filter or only.
But filter is also continuous
I
parameter.
assume there are finite.
Male or female.
Male or female? Yes, gender. Gender could be a hidden variable which will define, which will on which my distribution may depend on.
Language.
Language, very good. Language. What else? If I speak Telugu, then I will have certain kinds of patterns. If I speak Punjabi, it has certain kinds of patterns. Age, okay, yes. Age is a continuous random variable, but you can discretize maybe artificially saying that okay, between 0 to 10, between 10 to 20, like that. Or age range, something. What else? Phonemes. What you are saying. Did you say an A or E or U? I don't know. I'm just observing your MFCCs or frequency patterns, spectra. I don't know what underlying variables were there. Underlying phonemes were there. So like phonemes. Speaker. If all of you start speaking, then I have to tell, oh, who is speaking? Is it Sanreet or is it Shaurya or is it Shreya or is it Shreya? So there are so many hidden variables could be there. So the speaker identity, speaker ID could be one hidden variable. Okay, so with this we will bring our discussion to a pause. We will resume on Saturday. Yeah, but you have to kind of discretize it, so yes.